I will wait for 5 minutes. We'll see if people joins, or otherwise I will start after 5 minutes. There is an error here, so it should not be Friday, it is Saturday. March 2 is correct, but it's not Friday. Okay, let's start the session. In the meantime, people can join. I'll start the session by giving introducing myself. I am Ananya, a PhD scholar in the Department of Electrical Engineering IIT Kanpur. My specialization is microelectronics and VLSI. Welcome to the week 6 live session for the NPTEL course Semiconductor Device Modeling and Simulation that was taught by Professor Week6. So let's start the session. There might be some confusion because of the mail or the announcement, but the sessions are on Saturday. So this is the week 6, and in this week some of the concepts of MOS capacitor, MOSFET and ZFET, those were covered, mainly field effect transistors. So we will solve some questions based on those concepts. And these questions will be similar to the ones those are given in the assignment, so the sessions will help to solve the assignments also. Let's go through the first question. I will write down the question first. So the question is, choose the correct statement, and I will give four statements, four options. A, MOSFET is a current control device. That means whether MOSFET is a current control device, whether the input current controls the output of a MOSFET. Next is MOSFET is a temperature control device. Whether the input in case of MOSFET is temperature or not. Third statement is MOSFET is a voltage control device. And the last statement, the fourth statement is MOSFET is an uncontrolled device. Okay. So what will be the answer? Obviously the option 4, option D is not correct. MOSFET is an uncontrolled device because if we cannot control the output of a MOSFET, then output of any device, then it will not be very useful. And you know that MOSFETs are widely used in semiconductor circuits. Okay. So fourth option is obviously not correct, and among these three, so let me first draw a MOSFET structure, NMOS. So in case of NMOS, the substrate is a p-type silicon. These are the source and drain region. So for NMOS, these are N plus, sorry. And then this is the oxide layer, and this is the gate terminal. So these source and drain, these are symmetric. Let's consider this is source and this is drain. Okay. So what happens in MOSFET? The formation of the channel here. So there will be a formation of channel for NMOS. The channel will be of N type, that is there will be electrons in the channel, and the formation of the channel is controlled by the gate terminal. The voltage applied to the third terminal, that is the gate terminal, and that will basically lead to will give a current between source to drain, the drain current ID. That's how we get. So the correct option will be option C. MOSFET is a voltage control device because the applied voltage at the gate terminal controls the output. And what is the output? Output is the drain current. So let me write down that. MOSFET is a voltage control device. Okay. And here the gate terminal, that is the applied voltage VGS, controls the drain current IDS. Okay. If the output current, that is the drain current, that is modulated because of some other parameter or other voltage or any other parameter, that is undesirable. Okay, we want to control the output only by the gate terminal. What is the difference of this device MOSFET with BJT? So in last few weeks we discussed about BJT. So what is the difference? In case of BJT, let me write down first. It is a current control device. Okay. If it is a NPN transistor, so this is the emitter N plus, then I don't know the directions, I'm just giving random directions. So the base, we apply a small base current and we get the output current is IC. So it is a current control device. And here both types of carriers will flow. So both types of carrier means electrons and holes, both will flow, and that both types of carrier will actually contribute to the current, final current in the device. That is why these are known as bipolar junction transistor. That means there are two types of carriers. Okay, so these are bipolar device. Whereas MOSFET, these are voltage controlled, as we have discussed. unipolar device. Okay. For example, in case of NMOS, so this channel will be of N type. That means there will be electrons, and the current ID will contributed by the electrons in the channel. Okay, so this is a unipolar device. Let me see if anyone joined the meeting. Okay. Okay, let's go through the second question. So the question is on JFET. Okay, it is JFET, junction field effect transistor. A JFET has a drain current of 5 milliampere if IDSS is 10 milliampere and VGS off is minus 6 volt. Find the value of VGS and VP. So it is gate voltage, and for this drain current 5 milliampere, and what is VP? It is pinch off voltage. Okay. And the options are given in terms of volt. So let's first consider a cross section view of a JFET. So this is the source terminal, which is grounded, and this is the drain terminal, and let's say some voltage is applied here. Okay, VDS. This is the gate terminal, this P plus regions. Now this gate, this P plus N junction, this is generally kept as reverse bias, so there will be certain depletion region, and the depletion region will have this kind of shape because a positive voltage is applied here, so the width of the depletion region will be more in the drain side. Okay, these concepts were discussed in the lecture series. Now generally this is kept as reverse biased, and for a particular gate voltage, so this channel will pinch off. That means the width of the depletion region will touch here at the drain junction. Okay, so at this point basically the width of the depletion region is maximum here, and the voltage at which this happens is given as minus 6 volt. Okay, so gate to source voltage is reverse bias, that is why it is minus 6 volt. Okay, and that is why I considered an N channel JFET, because for N channel JFET, VGS off will be minus 6 volt, will be negative. Okay, so this type of device is given in the question. Okay, now the drain current is given as 5 milliampere and IDS is equal to 10 milliampere. So IDSS is the current when Vg equal to 0. Okay, when no voltage is applied to the gate terminal, the width of the depletion region on the both side will be minimum, and the current that will be flowing is written as IDSS. Okay, and it is given as 10 milliampere. VCS off is minus 6 volt. Okay, so by definition the pinch of voltage will be 6 volt. Okay, it's a pinch of voltage. Why I am writing VP as plus 6 volt? Because by definition pinch of voltage is a positive quantity, positive number. Okay, now you know the current expression in the JFET. Okay, current in JFET. By current I mean the drain current, because that is what we want. Okay, if we make this junction P plus N junction forward bias, then there will be a current in this direction also, but that is undesired. So that is why this junction, these two junctions are kept as reverse bias. Okay, so the current in JFET, that is the drain current, the expression is ID equal to IDSS 1 plus VGS by VP square. Now let's put all the values here and calculate VGS. We already calculated we already got to know that VP is 6 volt. Okay, now we have to calculate, so this is 6 volt and this we have to calculate using this equation. So this is 5 milliamp, 10 milliampere, 1 plus VGS we have to calculate, and VP is plus 6 volt. Okay, VP is a positive quantity. So this will be let me calculate this. VGS is minus 1.76 volt. If you consider the correct signs here, then you will get VGS is negative because we apply reverse bias at this P plus N junction. Okay, so here the correct answer is C, minus 1.76 volt and 6 volt. Okay, I have already discussed two questions, so I'll go to the third question now.
Sure.
So this third question is on MOS capacitor. So MOSFET and MOS capacitor, basically these two are different, like little bit different. Okay, so this question is on MOS capacitor, but the concepts are same for MOSFET also. Okay, the question is a MOS capacitor with silicon resin doping Na equal to 10 to the power 17 per centimeter cube, and intrinsic carrier concentration Ni is 10 to the power 10 per centimeter cube. Calculate phi f, which is Ei minus Ef by Q away from the oxide interface. Okay. Ei is this is the intrinsic level in the band diagram of a semiconductor, and phi Ef is Fermi level. Okay. Since Na is given, so it is Na is the accepted doping concentration, so it is a p-type substrate. Okay, for a p-type semiconductor, if this is Ec, this is Ev, this is the intrinsic level, which we consider approximately as the mid of the band gap. Then Ef will lie so this will be Ef, it will lie below the intrinsic level. Okay, so Ei minus Ef by Q is a positive quantity. So just by considering the band diagram, we can say that it should be, the answer should be a positive quantity, so these two are not correct. Okay, so let's go through this question. Okay, because this question is given as MOS capacitor, so I'll consider the band diagram of a MOS capacitor, although it is not necessary, because we can just simply use the semiconductor formulas and get phi f, that is the bulk potential. So this is generally we call as bulk potential. Okay, um, so it is not necessary, we can there is no need to draw the band diagram, but I will go draw the band diagram also and discuss few of the concepts. So it is a MOS capacitor, so there are three layers: metal, oxide, semiconductor. I will only draw the band diagrams, the the bands away from this interface. Okay, so for metal there will be a, so the band diagram of metal is described by the Fermi level of the metal, because in case of metal there is no concept of Ec and Ev, so this is say EFM. And away from the interface in semiconductor there will be no banding, so let's consider it's also a flat band condition, so maybe Ef is equal to EFM, and it is a p-type semiconductor. Say this is Ei and this is Ec. Let's take this as vacuum level. Okay, So these are energies, so the voltages will be, the potentials will be, this is the electron affinity q psi. Okay, from Fermi level to E vacuum, this is known as the work function. So this is q phi m. The notations may be different in different books, and I'm just giving you the overall picture. And we actually want to calculate this gap, okay, which is phi f, actually q phi f. Okay. So we can, as I mentioned, we can use the concepts of semiconductor. So for p-type semiconductor, Na is given as 10 to the power 17 per centimeter cube. Ni is 10 to the power 10 per centimeter cube. Okay. Since nothing is given here about temperature, so let's consider room temperature. So Kt will be 26 millielectron volt. Okay. Now the hole concentration, the equilibrium hole concentration, what I mean by equilibrium hole concentration, that is far away from the interface. Okay, even I am not considering any band bending here, so away from the interface, P naught will be that is the equilibrium hole concentration will be approximately equal to Na under certain assumptions. What are the assumptions? Where the doping concentration is much more than the intrinsic carrier concentration, which is true, and it is at sufficiently high temperature so that all the accepted atoms are ionized. And it is given as Ni exponential Ei minus Ef by Kt. Okay, this expression we already know. So from this expression, Ei minus Ef is Kt ln of Na by Ni, which will be 0.026 ln 10 to the power 7. I'm directly writing. Okay, and the unit will be the unit of Kt, which is electron volt. So this will be this is actually q phi f. Okay, so the answer will be 0.419 electron volt. Okay. So in the question we have to calculate in terms of volt. Okay. So that will be phi f will be, so bulk potential, so it is potential, so it is in volt. Okay, that will be 0.419 volt. So here the answer is A. Now a few more things I want to discuss. So what are these values, like the work function and electron affinity and other values? Okay, so let me write down here what is the semiconductor work function. So here I have written as q phi m. Sometimes it is written as phi s also because it's semiconductor. Okay, it can be phi s also. Okay, how we calculate? We can calculate using the band diagram here. And the electron affinity, this value is generally experimentally determined, and for silicon it lies between 4 to 4.1 around electron volt. Okay, these are common numbers, so you can remember. Let's take electron affinity as 4.05 electron volt. Okay, in many numericals these values are used. So what will be the work function? How we calculate it? Q phi s is Q psi plus this portion, which is the half of the band gap, Ez by 2 plus Q phi f. Okay, this is plus Q phi f because it is a p-type semiconductor. If it is an n-type, then it would have been minus. Okay, so the value will be 4.05 plus for silicon Ez is 1.12 by 2 plus, let's consider it as 0.42 electron volt. So the answer is 5.03 electron volt for this case. What is doping concentration? Okay, and the work function of metal will vary based on the doping concentration because the Fermi level will shift. So the Fermi level can be very close to EC. So in that case, the work function will be Q psi, and then the Fermi level can be very close to EV. So in that case, it will be psi plus EZ. Okay, so the work function for semiconductor will lie in this range. Okay, that is what I wanted to discuss. Even though the question is very simple, you can directly use this formula: P naught equal to Ni exponential Ei minus Ef by kT. Okay, let's go to the next question. Give me a minute first. Okay. Second theoretical question. Let me write down the question first. If a MOSFET is to be used in the making of an amplifier, then it must work in which region of operations? That is the question. First is the cutoff region. Second is the saturation region. C is triode region. Both cutoff and triode region. So let me draw the output characteristics for MOSFET. So in case of MOSFET, the input is the applied gate voltage and output is the drain current. Okay, if we plot the graph between ID versus VGS, then it will be transfer characteristics. We are taking one parameter from one of the side, either input or output, and the output characteristics we plot between VDS and ID, the drain current. So a typical ID VDS curve for MOSFET will be like this. Okay. These lines are when VGS increases for different VGS. Okay. So this is say reason 1 of operation, this is 2, and this is 3. So here reason 1 is known as linear reason, or triode reason. And the second reason, it is known as saturation reason, because current is saturated here. Okay. Or it is also known as active region. And reason 3, that is basically when drain current is 0, that is the cutoff reason. Okay. When the applied gate voltage is not sufficient enough to create the channel, to create the inversion. Okay. So there are two operations for BJT and MOSFET as well. These are either used as switch in digital circuits and as an amplifier in analog circuits. Okay. So to operate a MOSFET as an amplifier, so the MOSFET has to be operated in the saturation region. Okay. This you might have studied in some circuit course. I will not go into details. So for an amplification, MOSFET should be used in the saturation region. Okay. The MOSFET works as an amplifier in the saturation region. Both cutoff and triode region, this might be for switching operation. For cutoff, then the MOSFET will be off. Okay. Give me a minute. Let's go to the next question. Question 5. This is again on mass capacitor. So assume a mass capacitor with Na is 10 to the power 18. So it is a p-type substrate. Okay. And Ni is 10 to the power 10 per centimeter cube with an oxide thickness of 2 nanometer. So T ox is 2 nanometer. And Ks is 11.8. So what is Ks? This is relative permittivity of the semiconductor layer. Compute the depletion layer thickness W and electric field at the surface at the onset of strong inversion. So what it means by onset of strong inversion, it is the condition where phi s here is the surface potential. Okay. It is given as EI at bulk EI at surface by Q. So EI is the intrinsic level, and when the surface potential is equal to 2 phi f, that means phi f here is the bulk potential. So we have to calculate the depletion width and the electric field at the surface when phi is equal to 2 phi f. Let's draw the band diagram for a MOS capacitor. So metal oxide semiconductor. I am drawing first when these three layers are not connected. So the band gap for oxide is very large, so that is what I am indicating by this gap. Okay. And metal is characterized by the Fermi level in the band diagram. So this is E5. Let's say the other energy levels in the band diagram is here. So this is EC, this is EV, this is EI, and since it is a p-type semiconductor, so EF will be close to EV. In case of ideal mass capacitor, the Fermi level here in the metal side and the Fermi level at the semiconductor will properly align, but which is not the case for in most practical scenario. So there can be a band diagram like this for these three layers. So when these three layers are connected, somehow a connection between metal and semiconductor is established, then the Fermi level will be constant throughout the structure, and there will be some bending at this interface. Okay, let's draw that. Metal oxide semiconductor. Okay. So This is EFM, Fermi level at the metal side. This is at the semiconductor side. Away from the interface, the bands will be same, there will be no banding. So I'll try to draw the bands like this in a similar way. It is not scaled, but you can get the idea. This is EV, EI, EC. Now this Fermi level, to get aligned with this metal Fermi level, or this, so this will go below, so the bands will band like this at the interface. Okay. EI will also band and EC will also band. The oxide also, the bands will band like this. Okay. Now you can see there, because there is a band banding, there will be an electric field. Okay, whenever there is a band banding, in you see any band diagram, so that means there is an electric field. If the bands are flat, there is no electric field. Okay, so for example here, if there is an electron at this point, so because of the energy bands here, so it will move like this. Okay, so there that means because the direction of the movement of an electron and the direction of an electric field, these two are opposite, so that means there is an electric field in this direction. Okay, so whenever you see there is a band banding, there is an electric field. Now here this is the depletion width W. In case of ideal MOS capacitor, there should not be any depletion width. Okay, when no voltage is applied, no potential is applied, but for most practical cases there will be a band banding and there will be a depletion width even at 0 gate voltage. Okay. So now this difference is, let's say it is QV naught, which is equal to Q phi m minus phi s. Okay, the banding will depend on the difference between the work function of metal and semiconductor. Okay. Now we can use the formula for one-sided junction, PN junction or metal semiconductor junction to calculate the depletion rate. Okay, and there will be no the banding, the depletion width will be at the semiconductor, which is a p-type semiconductor. So it is a p-type silicon. So the depletion width will be in this region. Okay, in this in the semiconductor side. So the formula for depletion width is if you look at this formula, this is similar to the one that we use for one-sided PN junction. Okay, so here this is the potential difference at the interface. Okay, we are considering the reference point as EI, so you can actually take anything, but we are considering it with respect to the surface potential. So if the banding is more, so that is how it is related to the depletion width. Yes, is the permittivity of the semiconductor layer. So this is equal to permittivity in free space into Ks, which is 11.8 in our case for silicon. Now for ideal MOSFET, let me write it here also. QV0 is 0. Okay, this is when Vg equal to 0, which is known as the flat band condition. What was the question actually? Okay, so we have to calculate W. So for that we need to know what is the surface potential, and for the condition which is equal to 2 phi f. So we need to first calculate phi f, which is the bulk potential. Ni is given. Let's consider it as room temperature. So we have already got how we can calculate phi f. So let's do that. So what is the formula? Q phi f equal to Ei minus Ef equal to Kt ln of Na by Ni, which is 0.026 ln of 10 to the power 18. Yeah, 10 to the power 18 by 10 to the power 10, so it is 10 to the power 8, and the unit is electron volt. Bulk potential phi f is 0.479 volt if we write only as phi f. If we write in terms of electron volt, then it is Qf equal to 0.479 electron volt. Okay. So if you look at this, the bulk potential for this case is 0.479 electron volt, and in this question it was 419 volt. Although the doping concentration here is 10 to the power 17 and the doping concentration in this question is 10 to the power 18, one order different, but the bulk potential, these values are not very different because of the logarithmic dependency. So we got phi f, so we can calculate what is the surface potential, phi s, and we can calculate the depletion rate. Let's do that. Depletion rate when phi s is 2 phi f. Okay, so in the question it is given as phi s. I am more familiar with phi s as work function, and the surface potential is often written as psi s. So don't get confused if you see these terms, because these are essentially same. Just read whether it is work function or surface potential. W equal to, and if I might mix up these terms in between, so remind me if I'm doing so. So this is, the formula is 2 psi s. Okay, this is the formula, 2 psi s. So let's put the values, 2, which is 11.8 into epsilon naught, the permittivity in free space, that value is 8.854 into 10 to the power minus 14. I'm writing is in terms of centimeter because all other values will be centimeter. By all other values I mean NA. Okay, and it is 2 into 0.479. Okay, I hope it is 479. Yeah, 479 divided by Q, 1.6 into 10 to the power minus 19. NA is 10 to the power 18, square root of this term. So let's do a dimensional analysis also to see if we are doing it correctly. So the weight of the depletion region, so the unit should be in meter or centimeter or in something like that in terms of length. Okay, here this is unitless, this is farad per meter. So we are writing in terms of centimeters, so this is farad per centimeter, this is volt, this is coulomb cube, and this is per centimeter cube. So let me write here centimeter cube, and there is a square root. So there will be 1 centimeter outside, and farad, so this is the unit of capacitance. So C equal to Q by V, so that so farad will be coulomb by voltage. Okay, Q by V, so that will get cancelled with this V by C term. So final will we get the unit is centimeter. Okay, so farad is coulomb by volt. So what will be the value here? Let me calculate. So the answer is 3.537 into 10 to the power minus 6. This is in terms of centimeter. Okay, let me see the answer given. Okay, so answer is given as nanometer. So let me calculate in terms of nanometer. So this will be 10 to the power minus 2. So 6, 7, 8, and okay, 35.37 into 10 to the power minus 9 meter. So that is 35.37 nanometer. Okay. Okay. So there is only one option with this answer. So this might be the correct answer. But let's calculate the electric field also, so that we confirm that this is the correct answer. Okay. Again, the expression for electric field. So I'm using the formula from one-sided PN junction, P plus N or N plus P. You can check the formula. I'm just writing here. Electric field is equal to 2q psi s Na by epsilon s half. Okay, so in p-n junction, this instead of this phi s, there will be vbi minus v applied or something like that in terms. So this will be 2 1.6 into 10 to the power minus 19. Psi s is 2 phi f, so 2.479. Na is 10 to the power 18. S is 11.8 into 8.854 into 10 to the power minus 14. You can try the dimensional analysis by yourself, whether the unit is volt per centimeter or volt per length or not. Okay, we are writing in terms of centimeter everything. So the answer will be the answer is 5.4 into 10 to the power 5 volt per centimeter. Okay, everything is in terms of centimeter. Let me see. Okay, it is also given as in terms of centimeter. So yeah, we already got us 5.4 into 10 to the power 5 volt per centimeter. So our correct answer is D. Okay, so one more thing, we can calculate the electric field. So if you remember, the electric field in case of p-n junction, for abrupt junction, have a shape like this. So how we calculate the potential? We basically integrate. So potential is electric field, integration of electric field, right? So for this kind of triangular shape, what we have written earlier as what is the depletion width and multiplied by maximum electric field, right? We are considering it. We are considering the assumption that in mass capacitor it is like a one-sided junction. So the depletion width in one side will be very small in case of one-sided junction, and most of the depletion width will be in the lightly doped side. Okay, so in this case, what is the potential? That will be, so potential in our case is 5s, which is half of what will be the whatever the electric field maximum and without the depletion region. Okay, we know phi s. If you don't remember the whole expression here, you can use this formula also. So using this expression, electric field will be 2 phi s by w. the depletion region. And we already calculated these two parameters, okay, which is 2 into 2 into 0.479, okay, and W we have calculated as this. Let me write in terms of centimeter. Okay, let's see if we get the same answer or not. Okay, 3 point. So this is the answer is also same. I'm a bit confused. If you use this formula also. So if you don't remember this big expression, then you can use this assumption that we have already used for p plus n junction or n plus p junction. Okay. I hope it is clear. Okay. So you can see there are many information those are given which are not required. The oxide thickness to nanometer. So that is not required. But if we want to calculate the capacitance or the threshold voltage, then we need these information. Okay. So you already have these other parameters Na, Ni. Then maybe you can try to find the oxide capacitance and threshold voltage and all those terms. Let's go to the next question. So this is on CV characteristics. CV characteristics of MOSFET is very important. So we can get many information by looking at the CV characteristics, and to calculate many device parameters also the CV characteristics is used. Okay, so a CV characteristics is given as shown here. So we have to determine what is the type of the semiconductor. So it is given that the semiconductor is silicon and it is at room temperature. So what is the type of the semiconductor, whether it is a p type, n type, intrinsic? It is not a p-n junction because it's already given as mass capacitance. But let's see what is the type of the semiconductor for this kind of CV characteristic. Let me first draw the CV characteristics of a MOSFET. Yes, for MOSFET, and it is a NMOS. I'm considering a MOSFET, but it is same for my MOS capacitor also. It is similar, and the diagram I'm taking from the books Solid State Electronic Devices by Streetman. You can find it in any book. or it is given in the lecture material also, I think. So there are few reasons in the CV characteristics. Okay. So a typical CV characteristics for NMOS is like this. So the capacitance is high initially and then decreases to a certain value, and then again start to increase. Okay. So this point here, this is the reason accumulation. So for NMOS, the substrate is p-type, so accumulation means accumulation of holes. This point 2, this is the flat band voltage, this is the flat band, which is usually negative for so this is the negative side and this is the positive side, and this is the gate voltage. Okay, which is usually negative for NMOS. This region is the weak inversion region, and this is the strong inversion region. Okay. Let's say this point is 0 and VGS is 0 and this is VT. Now this is at when the frequency of operation is low. So this is at low frequency. At high frequency, this will be like this. Now if you can check what low and high frequency means in case of MOSFET, I don't remember the values, but you can check. Okay, what we can call as low frequency, what we can call as high frequency. Okay, and this is the minimum capacitance that a MOSFET has, which is denoted as C minimum. Okay. Now you can see that this curve is similar to the one that is given in the questions. So by looking at it also you can say that it is a p-type substrate, p-type silicon, where a n channel is formed. The inversion layer is the n layer, electron layer. Okay, but I want to discuss few of the concepts so that by looking at the CV characteristics you can get an idea. Okay, so in MOSFET the equivalent circuit will be equivalent circuit for the MOS capacitor, only the metal oxide semiconductor layer. I'm not considering the MOSFET like the source, drain and other capacitances, only these three layers. So how it is given, we can consider there are two capacitance. Okay, first one is the Ci or COX, that is the oxide layer or the insulating layer capacitance. So these capacitance are generally described as capacitance per unit area. Okay, so in some books it is written as Ci, in some other books it is written as COX, but these are same. The oxide capacitance and the semiconductor capacitance, and the gate voltage was applied in between, VGS. Now at point 1 here, so let's see that point 1. The total capacitance is only Ci or COX because the semiconductor capacitance, that is very high, and you know from circuits, if the capacitors are in series like shown here, then the overall capacitance will be given by the smaller number. Okay, at point 2 it is the flat band capacitance. Okay. And C minimum is the Ci by, okay, so this semiconductor capacitance has two parts. One is, so the equivalent circuit is like this is the depletion capacitance and this is the inversion capacitance. Okay. Cs. What is depletion capacitance? So in case of p-type substrate, so when the holes will be depleted, there will be Na minus ions, so that will give a capacitance Na minus and the gate voltage. Okay, so that is Cd is given as epsilon S by depletion width. Okay, W is the depletion width. And inversion capacitance is when the channel is formed and sufficient electrons are in the channel. Okay, in case of NMOS, then that will also give an inversion capacitance. Okay, so overall the capacitance, which term will be dominant, that will be determined by the charges. Okay, so you have already seen the charge distribution, how the charges are arranged in different region of operation, in accumulation, depletion, and weak inversion and strong inversion region. So based on that, which of this capacitance is dominant, that actually determines the CV characteristics of a MOSFET, and that's how we get CV characteristics like this in case of NMOS. Okay, here C minimum is Ci by CD minimum. Okay, CD minimum is when the depletion width is maximum, so Ci plus CD minimum. Okay. Now so at this point, by looking at the CV characteristics, you can see that at this point this is the oxide capacitance, and COX is epsilon OX by thickness of the oxide layer. Okay, epsilon OX, we already know the material we are using, say it is SiO2, and the thickness can be measured. So usually this thickness is very small, as we have seen in the last question, it was 2 nanometer. Okay, by from the value of the maximum capacitance at the accumulation region. Okay, and if it is a low frequency measurement, then in the strong inversion also we can get the thickness, which is very difficult to measure practically. Okay, so that is how, so that is why I mentioned that the CV characteristics for MOSFET is very important to get different parameters. Okay, and what are the other parameters those can be determined from CV characteristics that you can read? I think the doping concentration can also be determined. The flat band voltage or the flat band condition also gives certain information. Okay, but the let's go to the question that was actually given. So by looking at this, we can say that it is a p-type substrate, and here you can see this did not goes like this. Okay, so it is a high frequency measurement because it did not get enough time to create the inversion charge, and so that the capacitance actually rises. Okay, so that is why by looking at it we can see that it is a high frequency measurement, and here the accumulation is happening. Okay, so the maximum resistance, so this is COX. So the accumulation is happening when the gate voltage is negative. Okay, and the inversion is happening at when the gate voltage is sufficiently positive. Okay, so that means it is a p-type substrate. Okay, let me write down the conclusions here. It is a high frequency measurement. Next is accumulation occurs at large negative voltage. Okay, and at large positive voltage. By positive voltage I mean the gate voltage. Inversion occurs. And based on this we can say that it is a p-type substrate. I hope it is clear. I hope it is clear and I'm still in the meeting. Okay. Okay, let's do the next question. So here a MOSFET circuit is given. So till now we have considered the questions which are mostly related to the device. So this is a circuit. Okay. So the circuit is given here. The drain to source voltage VDS is VT plus 2 volt. Okay. Then what is the drain current ID in terms of Kn, and where Kn is mu n COX W by L. These are the device parameter. So how we will do this question? So you can see here the drain and the gate is connected, and the drain not the drain yes so drain and the gate is connected, and the drain voltage is given as VT plus 2. Okay, so this MOSFET is operating in the saturation region whenever you see the gate and these terminals are connected. Okay, so the device is in saturation region. And in saturation region, MOSFET drain current expression is ID, we write as half Kn VGS minus VT square. Okay, this is the drain current equation when it is in saturation region. Okay. Given as what is given? VGS equal to VDS. Okay. So this will be 2id by kn square root equal to vgs minus vt square root 2id kn. Let's take vt here plus vt. vgs is equal to vds and that is given as vt plus 2 in the question. Okay. So this is 2id by kn equal to 4. So id is 2 kn. Okay. Now you know what is kn, and so kn is mu1 cox w by l. Okay, you can do the dimensional analysis for drain current also. So what is the answer here? Answer is a 2 kn. I hope it is clear. Let's go through the next question. I will write it first. So which one is true when we draw an AC equivalent circuit of MOSFET? So the statements are: replacement of all capacitors by open circuit. Next is replacement of all capacitors by short circuit. setting of all DC voltages to 0, and setting of all voltages DC voltages to unity. So the options are A and C. These two are correct. Option B is B and C. C is B and D. And D is A and D. So what is the correct answer? This is the question is for a MOSFET, but in general this is true when we draw AC equivalent circuit of any device. So how we do this? We replace all capacitors by short circuit, and we replace all DC voltages by ground. Okay, when we do AC equivalent circuit. So that's how the capacitors and DC voltages behave in AC signal. Okay, so the answer is, so here this is true, B is true, and C is true. So the answer is B. B and C. Okay. In AC equivalent circuit, capacitors are short circuit, and AC voltages are grounded. Okay, is that true for any device? Okay. Let's go through this next question. This is on logic gates and circuits using MOSFET. So a circuit is given. So these are PMOS, okay, and these are NMOS. So it is a CMOS circuit, complementary metal oxide semiconductor. So this circuit, what it represents, which logic gate it represents: NOR, NOT, NAND, or AND. Okay, so I'm not sure whether it was discussed in the lecture or not, but I have seen there are questions similar to this question in the assignment. Okay, so let me give few details for the people who are not present in the meeting, who will be watching later also. We give some context how logic gates are implemented using MOSFET. Okay, logic gates using CMOS. So these are implemented using pairs of PMOS and NMOS. So these gates can be implemented using only one type of transistor also, and different other method. But why we use CMOS technology? Because by this way the power consumption is very less compared to other type of circuits. Okay, so how NMOS behave in this kind of circuit? So we have done questions on MOSFET or BZT using as an amplifier. So in case of gates, so these devices are used as switch. Okay, so how NMOS behave? So this is the circuit symbol for NMOS: gate, drain and source. Okay, this is VGS, and based on the gate voltage VGS, whether this transistor is on or off, that is determined. So it will behave like an open circuit if VGS is less than VT, or it will behave like a short circuit when VGS is greater than VT. Okay. Similarly, PMOS, how it will behave? The circuit symbol for PMOS is this. Okay, the arrow is here. This is gate, source and drain, and this is VGS. VGS is negative for PMOS, positive for NMOS. It is also denoted like this: PMOS. Okay, and NMOS is also denoted like this. So how it will behave in logic gates or as a switch? It will behave like an open circuit when VSG. So I'm using the conventional notation, whatever that letter that is written at the beginning, that is the positive terminal. So VSG is less than mod of VT. Okay, or it will behave like a short circuit if VSC is greater than VT. So that means the gate terminal has to be sufficiently negative compared to threshold voltage, and threshold voltage for PMOS is negative. So that's how MOSFET acts as a switch. Okay. Now how we can implement the logic gates? The first logic gate, that is the very basic one, is the inverter. Okay, so let's go through that. CMOS inverter. This is the PMOS here. This is the NMOS. And this is V in, the input voltage. And this is VDD, so which is, let's say, plus 5 volt. Plus 5 volt, plus 10 volt, it can be anything. It is sufficiently large voltage to drive these transistors or drive this MOSFET. And this is the output terminal, V out. So what will happen when V in is 0, which is known as logic 0? So VSG, what will be VSG? That will be greater than mode of VT, right? That is 5 volt. So VT is generally uh, some mode VT is close to maybe 0.7 volts, so it is sufficiently large, so PMOS will be on and NMOS will be off. Okay, so the equivalent circuit will be this plus 5 volt, this is short circuit, this is the output terminal, and this is open circuit. Okay, so the potential at this point will be essentially equal to the potential at this point. Okay, so this is approximately equal to supply voltage, which is 5 volt. Now it is a large voltage, so that we consider as logic 1 level. Okay, what will happen when V in is 5 volt? That means it is logic 1. In that case, PMOS will be off and NMOS will be on. The gate voltage for the NMOS will be 5 volt, which is much more than VT. Typical threshold voltage is around 0.7 volt. Okay, so the equivalent circuit will be, this is plus 5 volt, this is open circuit, this is V naught or V out. Okay, and this is short circuit, this is ground. So the potential at this point at V out will be essentially the potential at this point, which is the ground. Okay, so it is 0 volt. That means it is logic 0. Okay, so what will be the truth table? So V in and V out. So the truth table will be, if it is 0, then the output is 1. If it is 1, then it is 0. Okay, so this is the truth table for an inverter. Now similar concept is used to implement any logic gate, okay, or any boolean expression basically, but let me concentrate on logic gates. So how logic gates are implemented using CMOS technology? So there will be a supply voltage VDD, and this is a pull up network. Which is made from PMOS, and then a pull down network which is made using NMOS. The inputs are connected to both of this, and output is taken from here. Now why it is a pull-up network? Because if these MOSFETs are on, this will be off, so the output is connected to VDD. Okay, and when these MOSFETs are on, and so the pull-down network is on, then it will connect the output to the ground level. So these PMOS are generally grounded, so this will connect it, output will be connected to ground. Okay, now the gate that is given in the question, let me see. Okay, so how it is given here, VDD and the pull up network. So there are two PMOS connected like this, and the pull down network is like this. This is the input, first input A, and the second input B, and output is taken from here. So let's look at the truth table here. A, B, and V out. 0 0 0 1 1 0 1 1. Okay. So 0 means the input voltages are 0, and 1 means the input voltages are equal to VDD. Okay. So when A and B both are 0, so this NMOS will be, these two NMOS will be off, and these two will be on. Okay, the PMOS will be on. So V out will be connected to VDD, so output will be 1. Similarly, when it is 0 1, so this is on, this will be on, this will be off. Okay, and okay, B is means this is on, but this is still in off condition. So this point is not connected to this ground, but since this MOSFET is on, so it is still connected to VDD, so this output will be also 1. Similarly, for 1 0 also it is 1. When both are 1 1, so this PMOS, these will be off and these two are on, so V output will be connected to ground, so it is 0. Okay, so this is the truth table for a NAND gate. Okay, so what is V out? V out is A dot B bar. If you draw the K map and calculate it, then you will get V out as A dot B bar. That means it is a NAND gate. So the answer is C. Okay. So you will be able to draw based on this concept in OR, NAND, or any other gate. Okay, so if an inverter is connected at the output of a NAND gate, then it will be a AND gate. Okay, so if we connect a inverter here, so this will be A dot B. Okay, similarly you can make all other logic gates. Let's go to the next question. I will write down the question first. Body bias effect is used. So we have done some questions on circuits. This is again mostly on device. Body bias effect is used to adjust the threshold voltage of a MOSFET. under body bias, substrate, which is the body, actually body terminal is connected, substrate is biased with respect to what? Which terminal? With respect to source, drain, gate. So which of the terminal is connected? It's the reference terminal. Okay. Now how this body bias effect is used to change the threshold voltage? First I will write that. So for ideal case, threshold voltage Vt is given as minus Qd by Ci plus 2 phi. Okay, this expression I'm again taking from statement. You can refer to any book or lecture material. Okay. In general, if the bands are not flat, the interfaces are not ideal, then the threshold voltage is given as V flat band voltage minus Qd by Ci plus 2 phi f. Okay, here the flat band voltage VFB is given as the work function difference between metal and semiconductor, and the other interface charges, those are present inside the oxide layer. Okay, so be careful with the signs here. So I'll write down the so this is the depletion charge. Okay, Ci is oxide capacitance. So generally these are considered as per unit area. Okay, this is also maybe Cox in some book. And phi f is the bulk potential, and Qi is the oxide charge. Okay. Now, so as I mentioned, you have to be careful with these signs here. So again from statement, so I always remember this table. Okay, it is given there. So phi ms for most metal and and silicon junction, this is negative. Okay, and minus Qi by Ci, this is also negative. Okay, so this Qi, those are mainly positive charge, so overall this term is negative. Minus Qd by Ci, depletion charge. So this term is as a whole positive for n channel, and this is negative for p channel. Why it is positive for n channel? There is a negative term here that comes from the derivation, and for n channel MOSFET, so the depletion charges are Na minus. Okay, so the overall that is also negative, so overall term is positive. Okay, and 2 phi f Ei minus Ef, from that expression this is positive for n channel or p type substrate, and this is negative for p channel. Okay, I always remember this table. So that is why the threshold voltage for NMOS is generally positive and it is negative for PMOS. So I'll also, okay, let me not write here. Now how body bias effect is used to adjust the threshold voltage. So in general, let's consider an NMOS. I'll take few more minutes. Let's complete this. So this is N plus source, this is gate, so this is not gate, let's say this is channel. Okay, and this is drain, which is n plus. Okay, so the band diagram will be if there is no voltage drop, so this is the Fermi level. EC and EV will be like this because this is a P silicon. Okay, so the bands will be like this, and this is like this. Okay. So actually connected. Okay, okay, this is not very good diagram, but you can get the idea. Okay, so there will be flow of electrons between source and drain terminal that gives the drain current, and by the gate terminal this width is adjusted to change the change the drain current, and we want this height to be adjusted only by the gate terminal. Okay, now so when so this is generally reverse biased. Okay, n plus np junction, so that there is no unwanted current. So this is the body terminal actually, so this is VB. Okay, now when VB, so which is negative for NMOS, when it is applied, this barrier height actually increases, so that will increase VT. Okay, VT will also increase. And how VT changes? So delta VT is given by this expression. You can check QNA by CI 2 phi F minus FB half minus 2 phi F. Okay. Now if VB is very greater than 2 phi F, which is generally true, so delta VT will be 2 epsilon S QNA by CI minus VB half. This is for NMOS. Okay, and general. And similarly VT, let's for PMOS, let's write the negative sign here. CI VB half. Okay, so what happens for NMOS? VB is actually negative for NMOS, so delta VT is positive, so VT becomes more, so VT increases. Okay, when we apply, because the barrier height increases. For PMOS, VT becomes more negative. Okay, VB is positive here, so delta VT is negative, so already VT is negative for PMOS, so VT will be becomes more negative. Okay. So you got the idea how body bias is used to change the threshold voltage. Okay, and the body bias is, so basically all the voltages in MOSFET, those are written in terms of source. Okay, so the question was simply under body bias, substrate is bias with respect to what, but I have given you an overview of body bias effect. So here the answer is A, which is source. Okay. I hope it is clear. I will stop sharing, and it's already time is over, so I'll stop the meeting here.